Good morning, guys. It's me again, coming back with another biochem help video. Just before we start, a few little notes that I wanted to leave you guys with. Because you guys liked the last video, totally willing to make more. This is a great way for me to study. It seems to be helping you guys. So definitely a win-win situation. On the flip side, the rate that I can probably produce these videos as midterms approach is probably one video per week. That's just, I think, where I have to set the boundary for myself, which it seems like you guys are totally understanding of, so thank you for that. Which makes it seem like I'll definitely get this proteins and amino acids video out there for you guys, and most definitely a carbohydrate video out there for you guys. Lipids and lipids transport, and anything we do from there. I don't know if there will be a video out in time for that. So if you're going to spend lots of time trying to muddle through things on your own, maybe start there, and hopefully the videos that I make can help you prepare for these other topics. One other thing I want to point out is, as we move away from just the structure of basic macromolecules and more into the transport of them, that is an area that I myself haven't been very well educated in. So if there comes to be a topic that I'm not very knowledgeable in, I'm not going to waste everyone's time and pretend and try and make it up. So there may be times in the future where, as we go over a topic, where there might not be a video, and I'll try and let people know not to expect one. But I don't want to make everyone more confused because I'm trying to figure it out while I'm sharing that information with you guys. But yeah, so just keep, a heads up for those upcoming things. But before this video gets too long, let's start amino acids and proteins. So first things first, amino acid backbone. So everyone's taking the quiz now, and some people that I helped were really struggling just with the first question to draw an amino acid. And it makes a lot of sense why, because if you don't understand the structure of the amino acid, you're going to have a hard time drawing it. So before we just try and draw any amino acid, we need to understand this backbone, this common structure that all amino acids share. So what I just circled was the backbone. This is probably the easiest way for you to write and read the backbone. Every element is kind of drawn out. All the pieces are in a nice left to right, top to bottom order. And it's a great way to start practicing and understanding the structure of an amino acid. So amino acids have a couple different main parts, and these parts are going to be very consistent no matter what amino acid we're talking about. So moving from left to right, the first group I have in orange. This is the amino group of an amino acid. So without trying to teach everyone all the different functional groups in organic chemistry, just know that an amino group has a nitrogen attached to a carbon with some hydrogens attached. Don't worry too much yet about how many hydrogens are attached to that nitrogen. We will talk about that very soon, but begin to recognize a nitrogen bound to a carbon with some hydrogens is an amino group. And let me write that down. Wonderful. All right, moving in towards the middle, I just want to highlight this one central atom. It's just a carbon atom. And I'm just going to highlight the fact that it has a special name. We call this the alpha carbon. The reason I'm telling you this is just so when I call it an alpha carbon, you know what I'm talking about. So the alpha carbon is always the centralized carbon. It's what all the other pieces are going to be attached to. Moving down, just very briefly talk about this hydrogen. This hydrogen isn't super important. Remember, hydrogens are usually just placeholders in chemistry. So this doesn't really have any structural significance, but I just like to highlight it because it's there and it's going to be on every amino acid. All the way in the right in the blue is a carboxyl group. So we've talked a lot about carboxyl groups in class, but remember it's going to be a carbon double bound to an oxygen with an OH group as well. So this is our carboxyl group. I'll write that one down too. So carboxyl group. All right. And the last piece is the part that's going to change. So in chemistry, we have something that we can call a residue that we represent with the letter R. There's no atom that's represented by the letter R. R just means it could be a variation of things attached. So this is our residue. So when we're drawing the backbone of an amino acid, we're going to just put R, because it doesn't really matter what amino acid we talk about. However, as we move into specific amino acids, we can replace this R with a wide variety of different structures that's going to give that amino acid a different name, different property, yada yada. So this is the part that changes. Everything else is going to stay the exact same. So biochemistry in general is going to be a game of pattern recognition. It's going to be what looks similar and spot the differences. So as you are studying for amino acids, try to practice picking out these different parts. That's going to help orient you. It's going to help you understand the structure, what part he's talking about. So practice, practice, practice. Where's the amino group? Where's that central alpha carbon? Where's the carboxyl group? Okay, because I found those, I know what my R group is going to be. So down below, I drew out 4 different amino acids just for a little bit of practice. Now, I've condensed these a little bit because, as we talked about with our line angle drawings, it gets exhausting to write every single atom, but we can still practice the same concept. Where's our amino group? Remember our amino group, nitrogen, with some hydrogens attached to a carbon. And remember with our line angle drawings, if you don't remember those, go back and review them. There's a carbon right here, a nitrogen, and some hydrogens. So that means this is our amino group. All right. So the next easiest and probably the best thing to identify is going to be our carboxyl group. So what is a carboxyl group? A carboxyl group is that carbon doubly bound to an oxygen, singly bound to an OH group. Well, we can't really see our double bonds in the line angle drawings that I drew, but something I want you to just kind of more or less memorize is that when we take this drawing and we abbreviate it, when you see a coup, or maybe even a coup without an H and a negative sign, that's referring to these carboxyl groups. Just worry about memorizing that and not understanding that necessarily. But down here we see that. We see the COOH. That tells me that is our carboxyl group. All right, let's move on to the other parts. Always in between the amino group and the carboxyl group is that central alpha carbon. So if I find my amino group and my carboxyl group, in between is our central alpha carbon. Remember, we always have a hydrogen attached, but in line angle drawings, we don't like to write them out, but I'll just write it in this one time just so we can imagine it being there. And so that means everything else is our residue or our R group. So hopefully you recognize this amino acid a little bit. This is valine. This is one of the amino acids from the quiz. And the thing that makes valine rather than any other amino acid is this R group. this carbon-hydrogen structure that we see is valine. All right, moving on to asparagine. So once again, it's going to be pattern recognition in biochemistry. Where's the amine group? Where's the carboxyl group? Where's the central alpha carbon? And then where is the residue? Try and pause the video and identify them yourself. All right. Amino group, carboxyl group. Here is our centralized alpha carbon. I'm going to stop talking about that extra hydrogen for the most part at this point. Left behind is our R group. This R group means we have an asparagine because of the way it looks and the structure of it and the atoms that are in it. That's asparagine. No other R group is going to have the same exact structure from each other. All right, so those are two, I think, pretty simple ones to understand. Let's just highlight some maybe unusual ones. The first one is proline. So before I talked about proline and all of its special secrets, see if you still can't identify those patterns that we talked about in the previous two amino acids. Go ahead and pause the video and think about it. All right, so a little bit different because proline is so special, but we still have an amino group and a carboxyl group. In between those is always the central alpha carbon. So here's our central alpha carbon, and whatever's coming off that central alpha carbon is going to be our R group. Now, proline is the only amino acid that does this. It has a very special kind of ring-like-ish structure. And that is because proline is an imino or a cyclic amino acid. So the reason proline is so special is because it binds to itself. So its R group isn't really a true R group. As far as proline goes, we'll talk a little more about it in secondary structures. But this is one of the amino acids that if we have to memorize what certain amino acids look like by their R groups, proline will probably be on that list because its structure is so unique. Also, usually on a list of things that you would have to memorize, if we have to memorize them, is going to be glycine. Glycine is my favorite amino acid. I'm sure some people have heard me talk about it because it's unique and it's easy to write. So before we talk about glycine, try and find the patterns and think about it really hard. What do you think the R group or the residue of glycine is? All right, remember pattern recognition. Amino group, carboxyl group. The carbon in between them is that central alpha carbon. And we always said that whatever comes off that central alpha carbon is the R group. However, you'll notice there's nothing written off of that central alpha carbon. Go back to your rules about line angle drawings and think about it again if you didn't get it yet. In line angle drawings, what do we have? We have every end in a bend is a carbon, and we have ghost hydrogens. We've already talked about ghost hydrogens today, but they exist everywhere. So I just drew in my ghost hydrogens. Remember, this carbon only had 2 bonds written in, so we have to fill in all those other bonds with hydrogens. Now, remember, we are used to having 1 hydrogen attached. I didn't write them in on all of these, but they do have them. We see that hydrogen that we're used to here if we think about it. But we also have one here. So what's the R group? The R group in glycine, well, it technically doesn't have an R group, or you could call the R group this hydrogen. And now you're going to ask, well, how do we know it's the top hydrogen or the bottom hydrogen? Doesn't matter, just pick one. So glycine is my favorite just because it doesn't really have an R group. It's easy to write. It does lots of cool things to the structure of amino acids. But if you see just this one little bend and your amino group and your carboxyl group, you know that's a glycine. All right, moving on. So this is going to be really quick. I just wanted to point out, really practice, maybe even keep drawing them out as practice or keep looking them up and trying to read them. Practice that pattern recognition, because different people like to draw the different amino acids in different ways. They're still the same amino acids, but sometimes the way we orient them kind of scares us when we're not used to looking at them that way. But as usual, we have pattern recognition. So on this first amino acids at the top, can you find the amino group? Remember, nitrogen bound to a carbon with some hydrogens attached. Well, we only even have one nitrogen in this group. Here it is. Carboxyl group. That's always going to be a carbon doubly bound to an oxygen and also bound to an OH group. We only have that in one place here. So there's our carboxyl group. So in the next step, find the alpha carbon. Remember, the alpha carbon is always going to be in between that nitrogen and carboxyl group, like we had here. So we need to find a carbon that's attached to both of those groups. So let's work from right to left. So we have a carbon here, but remember that carbon is part of our carboxyl group. It's not attached to the amino group. That is not the alpha carbon. But if we move one over, we have another carbon here. This carbon is attached to the amino group and the carboxyl group. So this is our alpha carbon right here. And then anything coming off that alpha carbon is the R group, or the side chain. Down at the bottom left, pretty much what we're used to. However, it's just flipped in reverse, where our carboxyl group is on the left and the amino group is on the right, and our R group is down here at the bottom. I don't like this drawing. In the amino acid world, when we talk about amino acids, especially when we start to put them in a chain, we always talk about them from the N terminus to the C terminus. So N for nitrogen, C for carbon or carboxyl. So we usually try to write them, especially when we're writing them in a chain, with the nitrogen on the left and the carboxyl group on the right. But I just put it on here just so we can get practice looking at different things. But I kind of almost dare say this one's incorrect because of that. And then over at the bottom right, pretty much similar to what we had at the top. Here's our amine group, here's our carboxyl group. The carbon that connects both of them is right here, so that's our central alpha carbon. And anything coming off of that is our group, that's phenylalanine. Just letting you know that there's different ways to write these. Practice looking at them, practice the pattern recognition. All right, moving on to L versus D. So this is where chirality comes into play, so go back and review chirality if you need to, but it's actually pretty simple with our amino acids. The only thing we need to identify when it comes to chirality in amino acids is one, is it chiral? And two, is it L or D? That's the big question. So I just drew two generalized amino acids. I didn't specify which ones they are. I just wrote R for our group. One of them is L and one of them is D. So L is standing for laboratory and D is standing for dexteratory. Remember L for left. So let's answer question 2 before we answer question 1. So question 2 is asking, is it D or L? Well, how do we tell? Remember, we said L for left. So what needs to be on the left? The amino group. So I'm not going to get into the organic chemistry behind this, but when we're trying to determine L or D in amino acids, it's important that we orient our carboxyl group to the top. There is a scientific reason behind it. I'm not well versed enough to explain it, but for our purposes, we just need to know that that is facing upwards. And then it's as simple as, where is the amino group? Is the amino group on the left, or is the amino group on the right? If the amino group is on the left, it's laboratory. If it is on the right, it's dexteratory. The L form is the most important form because this is what we find naturally in our bodies. That doesn't mean that the D form doesn't exist. However, when we study amino acids, this is the one that we care about. That's all you really need to know about that, but let's go back really quickly and answer, is it chiral? So remember when we talked about chiral carbons, we had some requirements. That main requirement is that carbon had to have 4 bonds, and they had to be 2 different groups or different things. So I'm going to give you one hint, and it is there is only one amino acid that we've talked about that is not chiral. So pause the video, think about it, maybe go look at a list of amino acids. Can you figure out what amino acid is not chiral? All right, let me draw it for you. If you didn't get it before, can you get it now? The only amino acid that is not chiral is glycine. So glycine, remember, here's our amino group. Here's our carboxyl group. What is its side chain? Its side chain is technically a hydrogen. It also has another hydrogen down here as a space holder. So remember, our rule said we needed to have 4 different bonds. It does have 4 different bonds, but it's not to 4 different things. So glycine, we can't have an L or D form because it's not chiral. All right, so if you get an exam question that says, which amino acid is not chiral, that's your only answer option. Moving on. So this is a chart. There's a very similar chart in your notes from biochemistry, but this is just grouping amino acids together by some of their properties. Now, I do recommend you go back and look at Dr. Steiner's notes because he groups them differently than what I put here. This is just the one that I like to look at and the one that I used to use. We can kind of put them into groups in different ways, but when we're putting them into groups, we're going to put them into groups based off of their properties. So this chart groups them by 4 different properties. The first one is nonpolar. So remember talking about bonds very quickly. We had 2 types of covalent bonds. We had nonpolar covalent bonds and polar covalent bonds. So if those don't sound familiar, go back to my old video again. We can classify an entire molecule by those 2 properties based on how many of those bonds in that molecule are nonpolar versus polar. So if we have mostly nonpolar bonds, the molecule as a whole is going to have a nonpolar property, and vice versa. If it's got lots of polar bonds in it, it's going to be a polar molecule. So that's all that means. So all of these amino acids in the yellow group are going to be nonpolar because their R groups have mostly nonpolar bonds. Just a side note here, when we're talking about the property of the amino acid, the only thing that we're going to be looking at is the R chain, and so it's nice in this picture that all the R chains are highlighted for you. Because remember, all the other amino acids, the backbone is going to stay the same. So we need to focus on what the difference in the R group is to tell us what the property is and how it's going to behave. So we had the nonpolar, now we have the polar down here, and that just means that its R group has some more polar-y things in them. Some OH groups are probably going to be what you see primarily, maybe some carbon-oxygen bonds or nitrogen bonds in there. And then the last 2 groups, you also might see acidic and basic instead of negative and positive, but pretty much these amino acids, depending on their environment, could gain a charge. If we zoom in, we see these charges. Here's it there, and there. So we're used to probably seeing some charges on the backbone, but we can also have charges in the side group too, which is going to give those amino acids some extra special properties. We'll see how much we need to talk about that later, but just talking about grouping amino acids, once again, go back and review his notes. I think it's probably important that you study his version of the grouping. All right, this one it seems like everyone's pretty confident in that I've talked to so far, but we do know that some amino acids are essential and some are conditionally essential. I just put the list on here. If it's on this side of the list, it's essential. If it's on that side of the list, it's conditionally essential. So remember, if it's essential, we need to consume. It is essential that you consume it. And that's because our body doesn't produce it. Remember, we use amino acids for a lot of different reasons in our body. So we need to either produce them or consume them. So the essential amino acids, is essential that you consume them. We have a smaller grouping in this conditionally essential. That means, yeah, it's probably a good idea that you eat them too, but if you don't eat them, you're not gonna die because your body knows how to produce them itself. It can take other molecules or sometimes other amino acids and produce these guys from that. All right, moving into some beefier stuff, we have how pH changes the structure, and we're mostly going to be focusing on the structure of the backbone in this class and less the R group. But you should know that depending on the pH of the environment, the backbone might start to look a little bit different. I'm sure you've started to notice this so far. So there's just three states that we need to understand in this class. That's first the basic state. So remember, that's going to be our very high pHs. And in the basic state, it's going to give our backbone a positive charge because there's going to be 3 bonds to nitrogen. So something to remember is nitrogen likes to have 3 bonds. Now we talked about carbon needing to and only ever having 4 bonds. Some some atoms are a little less picky and have a preference but can make more or less depending on their environment. Nitrogen is one of those. So nitrogen, well, likes to have 3 bonds. It can form 4. However, when it forms 4 bonds, it's going to have this extra positive charge written with it. Think about the plus being just like plus an extra bond. Moving down to our acidic state, you're going to see a negative charge instead. So acidic environments, that's going to be lower pHs. And oxygen's also kind of like nitrogen where it has a preference, but not a hard and fast rule. So oxygen likes to have 2 bonds. And I'm just going to draw this structure out a little more so we can see what's going on here. And in this acidic environment, this hydrogen left. So now this oxygen only has 1 bond. So you can think about negative like missing a bond. And lastly, we have the important state that we've talked about. This is the one that I would highlight. This is the one that was on the quiz. You should know the term Zwitter ion. So remember, ions are a molecule that has a charge. A Zwitter ion is a molecule that has multiple charges, but the specific rule is going to be that the charges cancel out. Or they're going to have a net 0 charge. So if we add all the charges up together, it's going to equal 0. So in this form, our nitrogen is going to have those 3 hydrogens with its plus charge. Our carboxyl group is going to be missing its hydrogen with its negative charge. Plus and a minus is a 0. So that is a Zwitter ion. He told us to associate that with a more neutral state. Personally, I don't know that I agree with that. Seeing Zwitter ions, I don't think that's a natural occurrence, but I could be wrong. but know what a Zwitter ion is, know how to write it out, know how to recognize it. Remember, pattern recognition is important. So if you see both of these charges, Zwitter ion. All right, moving on to how to link an amino acid. So when we want to link amino acids, we're starting to move into our topic less of just amino acids, more of proteins as a whole. We need to form a peptide bond. So peptide bonds, peptide and protein, right? Peptide bonds are going to link amino acids together, and something you should kind of commit to memory is these peptide bond formation processes are condensation reactions. So what's a condensation reaction? Well, let's think about what condensation is. When you leave your ice cold drink out on your desk, water is going to form around the cup. And we say, oh, that's just the condensation. So condensation is going to equal water formation. You can also call this a hydrolysis reaction. So we need to form water to link these amino acids together. So what is water? Water is simply H2O. So the easiest way to think about this is we need to go in. I have already conveniently lined up these amino acids next to each other, and we just need to find the ingredients for water and pull them out. So to form water, what we really need is not just two H's and two O's. We need an OH and an H. Don't worry too much about that, but it is a technicality. So if I go in between these amino acids, we're going to pull them from this area because this is where they're lined up next to each other. I first see my OH, so I'm going to get rid of that first. The OH is always going to come from that carboxyl group. And then we're just going to pull another H off of this nitrogen. It doesn't matter which one. So we've just formed water. Well, let's think about what was left behind. We have a carbon here that now only has, I'm sorry, there's not a carbon there. I just didn't erase very well. We have a carbon here that now only has 3 bonds, so it's unhappy. And we have a nitrogen here that now only has 2 bonds, so it's unhappy. So how can we make these two molecules happy? I'm going to bring them closer together. This is going to look a little awkward because of the way it's drawn. I'll clean it up in a minute. But we're going to form a bond between that carbon and a nitrogen. This bond right here is the peptide bond. So let me just move some things around just so it's neat and tidy. But here you go. You've just linked your first 2 amino acids together. You just formed a dipeptide. Di meaning 2, peptide meaning there's a peptide bond connecting them. So of course you can keep doing this over and over and over again until you get a tripeptide and a tetrapeptide, and eventually we just give up and start calling it a polypeptide. So as you practice this, find some pictures of polypeptides, or you can use a website I like called PepDraw, where you can just give the website a list of amino acids and they'll draw out your polypeptide for you, and go back through. See if you can find where these peptide bonds are. And once again, it's going to be pattern recognition. Finding that amino group, finding the carboxyl group, finding the amino group of the next amino acid. That bond between the carbon from that carboxyl group and the nitrogen from the amino group is where that peptide bond is always going to be. So pattern recognition and practice. So let's move on to proteins themselves. So remember, polypeptides, that leads us right into proteins. So we have different levels of protein structure, from, simple to more complex. And I'm going to start just by listing out these different levels of structure, and then we can go back and talk about them. So first we have primary structure, and that is just our string of amino acids. So really what we were forming back here was the beginning of our primary structure. It's just telling us from left to right, from N terminus to C terminus, what amino acids do we have in what order. So is it glycine, cysteine, phenylalanine, or is it histidine, glutamate, asparagine? Our secondary structure is much more exciting. We have two secondary structures. We have alpha helices and beta pleated sheets, and those are named by what they look like. We'll talk about how those form. We also have something we can talk about during that time called loop regions. More on that later. But we can take our string of amino acids, we can wrap them up or fold them up, and that's going to make our secondary structure. Third is our tertiary structure, and that's the bundling of secondary structures. So if we have 3 alpha helices and 2 beta pleated sheets, how are we going to arrange those near each other to make a tertiary structure? This is really where we get into the functional unit of a protein. These aren't really true proteins. They're the building blocks, they're lower levels of structure, but when we make our tertiary structure, that's when it becomes functional. Now, not all proteins will function in a quaternary structure, but quaternary structures are super important and they do exist. Sometimes we have multiple tertiary structures that work together kind of as one big unit, so we have many subunits, and they work together to function as one major protein. All right, so let's go back to those primary structures. Remember, we're going to talk about the bonds that form these different structures. So our primary structure is a string of amino acids, and here's the important part, linked by peptide bonds. This is why peptide bond formation is so important. So here's a nice little polypeptide, very nondescript, and then they blew it up here so that each little ball is its own amino acid linked by peptide bonds. So go ahead and pause the video if you want some more practice. Find where each of your different amino acids lie. See if you can identify the amino groups and the carboxyl groups. I mean, they're going to look a little bit different because they're now linked by peptide bonds. And then see if you can identify where those peptide bonds are. So that is your primary structure. Moving on to secondary structure. This is, do we have alpha helices or beta pleated sheets? How do those form? What holds these structures together? They are formed by hydrogen bonds in the backbone. Emphasis on in the backbone. So we're going to see hydrogen bonds again when we talk about the tertiary structure, but we're going to see them between the R groups. When we're talking about secondary structures, we just need to worry about what's happening in the backbone. So go back, review hydrogen bonds if you need to. But I'm going to give you a shortcut. The places where hydrogen bonds can form is going to be one of the hydrogens attached to your amino group and the doubly bound oxygen from your carboxyl group. Now, the ones that make the hydrogen bonds, they're not going to be adjacent pairs. They're going to be kind of distant neighbors. And I'm going to do like a little bit of a demo. Hopefully I can sneak it in here if my editing skills are good enough to kind of show you what I'm talking about when I'm talking about these hydrogen bonds in the backbone. Alright, here's that demo on secondary structures of amino acids. Let me back up a little so you can see me better. So I did this demonstration for some classmates and they seemed to say it made sense. So remember, secondary structure, hydrogen bonds between pieces of the backbone to form an alpha helix or a beta pleated sheet. So, what do we need to form a hydrogen bond? We need a partially positive hydrogen and a partially negative atom. So if we just focus on the backbone of the amino acid, easy to find the partially positive hydrogen. It's going to be the one attached to the nitrogen of an amino group, which I'm representing on my charger cord with a rubber band. So this is a partially positive hydrogen on the nitrogen of an amino group. And down lower I have a black hair tie. This is representing my partially negative atom. Can you go and figure out, before you keep watching, what is the partially negative atom just in the backbone that we could be talking about? Well, if you figured it out or if you didn't, it's the doubly bound oxygen to carbon. So here is my primary structure of an amino acid. Remember, our primary structure is just the chain, it's just the lineup. And remember, I have these two important parts marked: partially positive hydrogen, partially negative oxygen. So remember, our ribosomes produce our protein, so when this nice primary structure shoots out of our ribosome, it's going to go probably into the cytoplasm. And it's going to start flinging around, really. There's going to be other proteins kind of helping this process along, so it's not super random. But what's eventually going to happen is this partially positive hydrogen is going to line up on top of this partially negative oxygen, and a hydrogen bond is going to form. You can imagine how this could happen multiple times. I'm sorry I only have two hands, so I can't do this very well. But here I've kind of formed a little bit of a, hopefully what looks like an alpha helix. Imagine there's like another, hydrogen-nitrogen situation happening around here. But it's these hydrogen bonds in the backbone that can form the structure. We could do the same thing with a beta sheet, right? We could fold this over, and these are going to hold on to each other with a hydrogen bond. We can fold it again this way and this way. Bada bing, bada boom. That is your secondary structure. Just an important note before I go back to these slides, especially when we're talking about these alpha helices, something that I've heard Dr. Steiner bring up before is that, remember, I kind of already mentioned it. These hydrogen bonds, they're not going to be from next door neighbors. Notice how far apart these guys are. There's multiple other amino acids in between. So it's not going to be like a little kink here between the amino group and the carboxyl group on the same amino acids. There's going to actually be probably around 3 to 4-ish R chains in between these two spots. So if we take all the turns of an alpha helix and I count how many R groups I see in each kind of swirl of the alpha helix, you're going to count somewhere between 3 and 4. It's going to vary a little bit. Hopefully that helps you understand secondary structure. Okay, so hopefully I got that video in there. Moving on, very briefly, just to talk about a loop region. So a loop region is just these 180 bends. We see them mostly with our beta-pleated sheets, but it's where our protein is going to kind of just make a turn. And the thing that you need to know about loop regions is it's a 180 bend, and that there are 2 amino acids that can cause them. There's only 2. So if we have a proline or a glycine in our primary structure somewhere, it's going to be at those amino acids that we're going to see that 180-degree bend, or the loop region. Think about the shape and size of these amino acids. If we go back to my first slide, these amino acids have little to no R group. I mean, this one has one, but it's nice and tucked in, and this one barely has one because it's just a hydrogen. It's shape and property that allows loop regions to form around them. Right, moving on to tertiary structure. So tertiary structures, we're going to take all those secondary structures, and now we're going to bundle them together. So we're taking all these alpha helices, all these beta-pleated sheets, and we're going to kind of put them into a ball together. What holds them together is going to be interactions in the R group. So before we were talking about the backbone, now we can finally look at the R group. So remember, we talked about all those different properties that these different amino acids can have. It's these properties that determine our tertiary structure. So we talked about a small list of interactions and bonds that can cause tertiary structure. The first one is a disulfide bond. So think about what that name means. It means 2 sulfurs. So for a disulfide bond to occur, you're going to have 2 cysteines. So it's going to be a nice rule for you to remember. 2 cysteines are going to form a disulfide bond. It's still just like a covalent bond. Nothing too special, but because of what it kind of does to the tertiary structure, which we haven't talked about, don't worry about, we do give it a special name, and we do like to list it separately from just like a covalent bond. We could have hydrogen bonding. Remember, we talked about hydrogen bonding forming the secondary structure in the backbone, but when those hydrogen bonds form in the R groups, that can also contribute to tertiary structure. Down here he listed as salt bridges. I prefer talking about ionic bonds. They are almost the same thing. And hydrophobic and philic interactions, that could also be equated to nonpolar and polar interactions. So these polar groups are going to be your hydrophobic. They're not going to like water. And these guys are going to form a nice little clique, and they're all going to want to hang out together. Your polar ones are going to be your philic. They're going to like water. So these guys are going to form a clique and hang out together. So these guys like to hang out together, and these guys like to hang out together. They do not like to mix. So those are going to be your hydrophobic and philic interactions. All right. And like I said before, we're now in the functional form. This tertiary structure can function on its own as a protein. Or, in some cases, we're going to form a quaternary structure or a globular protein. So this is going to be many subunits. So, maybe 1, 2, 3, or more of these tertiary structures bound together working as one group. So this is where we have the terms. We can say di, tri, or even tetrameric. This is telling us how many of those subunits we have in our globular protein. So the example that I love that we talked about in class, he gave a couple examples, but I like hemoglobin. Here's a nice pretty picture of hemoglobin. Each subunit is represented in a different color. And so that's just a great way to visualize how we can have 1, 2, 3, 4 tertiary structures forming one quaternary structure. And because there's 4 subunits, that would technically be a tetrameric protein. Something I just highlighted down here, I don't know how important it will be for an exam, but he did spend some time talking about histidines are in your primary structure of these subunits, and it's going to help hold the quaternary structure together. I think the point that he was trying to make here is sometimes it's just certain amino acids, maybe another metal ion that we associate with it, like an iron. Those can play a role in holding a quaternary structure together. Alright, so I'm going to skip the nutritional information because this video is already getting very long. But it was in his slides. He talked about what a perfect protein is. He talked about malnutrition conditions, and he talked about digestive enzymes. Remember that you just need to remember the site of the activity for all those different enzymes. And the last part of this video, I'm going to rush through pretty quickly because I think some of the things you were talking about is kind of going over heads, because we look at this, and even I'm looking at this and I'm thinking, wow, this is a lot to look at. What do all these things mean? I think what he kind of didn't do for me was emphasize what is the highlight, what is the takeaway. So the first thing we want to talk about is the transport of amino acids. So if we digest an amino acid, we need to bring that into our cell to be used. That's why we eat amino acids. They're going to be building blocks for other things in our body. But there's an important step that needs to happen if we're going to do this. If I just bring this amino acid into the cell, there's nothing stopping it from going out of the cell. So one of the first steps that we see in this big circle that's very intimidating is that we're adding a group to our amino acid. That group is just ensuring that the amino acid doesn't float back out of the cell. Another point that he made was that there's going to be something called a transpeptidase. That is another protein, and that's what we call a chaperone protein. Think about what a chaperone does. It kind of goes with you on a date to make sure you don't do anything too nasty to each other. A chaperone protein accompanies a molecule that is trying to transport to make sure it knows where to go, essentially. So the chaperone protein is going to bring the amino acid into the cell. We're going to attach stuff to it so it doesn't float back out until we have a chance to actually do what we need to do. Next, he talked about trans and deamination. These words kind of sound like what they mean. It means we can transfer, or D means to get rid of, an amino group. So these are just pictures of trans and deamination. We're either transferring the amino group from one amino acid to another, or one molecule to another, or we're just getting rid of it completely. Here's why he brought it up. Here's why it's important, at least in my opinion. It's going to be the first step in breaking down amino acids. So when we have amino acids, when we digest them, we need to break them down to actually be able to use them. This is always going to be the first step. So if we ever do move into amino acid catabolism, or the breaking down of amino acids, this is going to be the first step that we see. And this leads him into his kind of final points that he talks about. When we do this process, we're going to start producing these NH4s, these ammonia groups, and we kind of hopefully know by now that this is toxic for our body, and this is why we need the urea cycle. So he talks about the urea cycle here. Here's just a picture of the urea cycle. Don't worry too much about everything that's happening in it, but I highlighted the important parts. See how we have this NH4? This was because of a deamination. Well, now we need to get rid of the NH4, and that's why we have the urea cycle. We're going to transform this NH4 with a bunch of different steps into a urea. So urea was something that he talked about a lot. You can go back and review the end of his PowerPoints. He talks about the ureas of what happens when there's too much urea in the body, how that causes gout, how it causes other bodily conditions. He also spends a little time talking about why the urea cycle is important, because remember, if you don't have urea cycle, you're going to have a bunch of these NH4s floating around. That's going to cause your body to go into failure. So don't spend a lot of time trying to learn all these different molecules or the processes here. I mean, we'll see when he writes his exam and gives us a study guide, but just focus on the highlights. What is the reason for these things? Alright, so that's the end of my video. I hope you guys enjoyed. Hopefully by around this time or over next weekend, I will make a carbohydrate video for you all.